In this lecture, we talk about sensitivity analysis about linear programming solutions. Sensitivity analysis refers to post-optimality analysis, or we say parametric programming or optimality analysis. So when we mainly look into the effect of changes in three areas in your linear programming models. So first, objective function. So in the objective function, you can actually see if we change the parameters, then the optimal solution may be affected or may not be affected. So the parameter we talk about is mainly objective function coefficients. And we also look into the right-hand side values in your constraints, and then constraint coefficients. Here you can see the constraint coefficients actually will not be addressed in this lecture. So we will only focus on the objective function coefficients and the right-hand side values. So the problem we look into is assume you have a LP model, you have solved the model, get some solutions, already obtained the optimal solution. But now the coefficients on the right-hand side may change due to the change. So how the optimal solution will be affected. So that's the problem. And then in this condition, we address a series of what-if questions. So the sensitivity analysis actually does not require to resolve the problem. So we look into the problem data and your further information from Excel solver, then you can actually make a judgment. So here we use a complete case to talk about to introduce the sensitivity analysis result of the method. So let's see, this is our original LP model. So given the parameters in the tables and the LP model formulated. So this is the model, and then we can use the solver to solve this model. Before we look into the Excel solutions, we introduce another concept in the LP models. So we write your original LP model. So this is the original formulation of your LP model. We rewrite this into a equality system. So you can see now all the inequalities, not this. So go back. So you can see the inequality constraints now actually changed into equalities. So this is this has been done by adding slacks. So here S1, S2, S3, S4, they are the snacks. So we can take one example, XA plus 2 times XC plus S1 originally should be less than or equals to 120, and now we add one S1 non-negative value on the left hand side. Then it's possible to change this inequality into a equality. So the same idea, we transform the inequality system into a equality system. So here the S1 and S1 until S4, they have their meanings. So you can see we define S1 as the number of hours not used in the department 1. So basically leftover extra capacity. And S2, number of hours not used in department 2. S3, surplus capacity of the model S2. And so S4, surplus capacity of model Cosmo. So now we know the meaning of the slack variables. So we call it slack variables. When we use Excel solver to solve the LP models, you actually can see in the result window, you see there's options you can choose to show answer report and sensitivity report. So here this page shows you the answer report. So now let's see the content in this report. So in the answer report, we actually can easily find the value for Slack variables, which is in the last column of the constraints table. So now you can see in the department 1, you have extra hours left. In the for the product customer, you have the extra capacity, 30 units left. So that's how you actually can find the extra values. And you can see if you have extra positive capacity existed, then you actually can see this constraint 1 for department 1 production hours actually is not bending. So if the slack variables is 0, then that's bending. So continuously you can see all these constraints, which one is bending, which one is not bending. Apart from the answer report, you can also get the sensitivity analysis report from the Excel solver. So now you can see this report includes 2 parts. First one is about the variable cells. So you basically can see the optimal solution directly in the variable cells. And the constraints, you actually can also see the final usage. So basically this value is the quantity you actually used in left-hand side. So that's about the sensitivity analysis report. There are a lot of other information available. So today we are going to address how to actually interpret the values and how to use these values to make a judgment about changes of the parameters to the optimal solutions. In this report, you actually can also see since here is your B constraint right-hand side, and this actually is the final values. So the difference between these 2 columns actually is the slack values. So we first talk about the effect of objective function coefficients changes. So the question is how much an objective function coefficient can increase or decrease without optimal solution being changed. In this case, we actually assume that each time only one coefficient is changed. When you have to combine that, then you have to use other series. So we start with a single coefficient change. And here we have 2 small points you may have realized that. So if you remember how to solve the LP model by the linear program, by the graphical method, you know actually the feasible region. So this is a feasible region, and if you change the objective function coefficient, then this region will not be changed. And what changed is actually if we use a right curve to show the SFO line of your objective function. So if this is objective function SFO line, and then you actually change the slope of this function. So you can just think about now if you change the coefficient, maybe your SFO line will become more steep or more flat. So this is the change you can think about. So we only change the slope, not change the feasible region. In this slide, you see a better example with the specific formulas. Now you can see in the if we see this is a figure A. So this is figure B. In figure A, you have our original objective function. So now if the coefficient for XA is increased to 40, then you can see the SFO line of objective function become steeper. So then when you change the coefficient, this line's slope changed. That's what we basically would like to show you. in this example, you actually can see the optimal solution is not changed, even though you increase the coefficient, you doubled the coefficient of decision variable xa. But we also would like to see when this optimal solution will actually be changed. We do not suggest actually to resolve the original IOP model, because if your IOP model is large, it actually takes a lot of time to solve once your model. So if you can get some direct information from your solution, then we should just directly use the output from your Excel solver then to conclude some conclusions. So now let's see the example in our Tele computer example, company Tele mini case. So in this slide, we see if the coefficient of xa increase. So we increase the value. So the original coefficient for xa actually is 20. So if we increase this value, and then the optimal solution may change or may not change, how can we actually conclude this? So here you can see, if we increase the coefficient of xa, the slope of the objective function becomes steeper. For example, previously we increased from 20 to 40, and then you can see we have output from your sensitivity report called allowable increase. Now you can see whatever you increase, so your optimal solution will not change. They will remain as the 70-20. In this case, we see actually from the results, allowable increase for coefficient of xa is 10 power of 30. So that actually means you can increase to infinite. The optimal solution will not be changed. So that's basically what we wrote in the third part. So now you can see we focus on allowable increase in your sensitivity report. So this is a sensitivity analysis report. So on the other hand, now let's see if we decrease. So if we decrease the coefficient of xa, what's going to happen? So you can read the text in the slides. It's very comprehensive. So I just quickly see here. You just need to look into the allowable decrease column in your sensitivity reports in the variable cells. So here the value of 10 means if you increase the coefficient, if you decrease the coefficient of xa until 10 units, your optimal solution will not be changed. So we can take an example. If you decrease the coefficient of xa from 20 to 15, so optimal solution will not be changed. And if you try to increase this 20 to even lower, for example to 9 or to 10, then the decrease number will actually more than 10 units. Then your optimal solution will change into 60-30. So then we can see that the allowable decrease for coefficient xa is 10. So that's actually the boundary for you to change the coefficient without changing the optimal solution. So in this case, you know this when your xa's coefficient from 20 become a 10, you may have two solutions. So 70, 20 and 60, 30, basically the SO line of objective function parallels with your boundary on the feasible region. So that's why we got two solutions. So actually, all the solutions on the boundary line, they're all optimal. So actually, you reach multiple optimal solutions. Now let's see how much the coefficient of xc in the objective function can increase or decrease before the optimal solution changes. So now you can see the allowable increase and allowable decrease for your decision variable xc in the two columns in variable cells. And then you can actually see xc's coefficient, so if you call it a cc or something, can change to decrease to 0 or to increase to 20, because you have both allowable increase and allowable decrease of 10, then the optimal solution will not be changed. And the next question, will changing the coefficient of xc in the objective function can change the optimal value? This actually is another question. So you just, if you remember your objective function, to maximize zeta equals to 20xa plus 10xc. So you actually can see now your function become actually another value. For example, you increase the objective function of c into 15xc, because the optimal solution is not changed. So xa is still 70, xc is 20. So you actually got a new optimal value, 20 times 70 plus 15 times 20. So actually your optimal value will increase. So on the other way, if you decrease the coefficient, your optimal value will also be changed. So okay, now let's come to the summary about objective function coefficient. So changing an objective function coefficient will not influence the feasible region. We talked about that. It's only the slopes of the objective function changes. Changing an objective function coefficient within a allowable increase or decrease range under variable cells, as shown in the sensitivity report, will not change the optimal value. So highlight the allowable increase or decrease in the sensitivity report. However, the optimal values changes. So that's several important hints you should remember. So in this example, we look into a new concept, a new result in the sensitivity report called reduced cost. So you can find the value in the reduced cost column. So now we take an example. So assume that after some detailed calculations, the manager has found that the production cost of Cosmo TVs is underestimated by 15 units. So for example, that maybe production cost of Cosmo is underestimated by 10 units. And then that means actually the marginal contribution for Cosmo TV now is minus 5 kroner. So you can find this value. Now you have a new objective coefficient, minus 5. Now, if we require to produce at least 1 unit Cosmo, we will lose 5 kroner. So if the coefficient of xc is increased by 5 kroner, we will not lose anything by producing Cosmo TVs. So that's actually the information you can read in the reduced cost. So this minus 5 means you actually now need to at least increase your objective coefficient by 5. Then you actually can at least get a value for xc which is positive or not 0. This sounds a little bit puzzled, so we can see more in the following slides. So we continue to see the reduced cost in your sensitivity report. Now we can see for xc, your solution is 0. So xc has a value equals to 0 in the optimal solution. within a new coefficient. So the reduced cost for xc takes minus 5. Then we can see this reduced cost minus 5 shows that the value that the coefficient of xc in the objective function must be changed by before xc obtains a positive value in the solution. So now that just shows if reduced cost is minus 5, that means you actually need to reduce the cost in your contribution margin in order to increase your contribution margin by 5 units. Now we actually take a summary for the reduced cost. So the first one is a very what we tried to explain. For a variable with the value 0 in the optimal solution, the reduced cost is the value that the corresponding objective function coefficient must be changed by before the variable obtains a positive value in a solution. So for a variable with the value of 0 in optimal solution, so same situation, the reduced cost indicates the shadow price for the non-negative constraint. We'll see that later after we introduce shadow price. For a positive value variables in an optimal solution, so here we're talking about positive, for example, xa, the reduced cost indicates the shadow price for simple lower upper bound constraints. So if a variable lies between its simple lower upper bounds in an optimal solution, the reduced cost equals to 0. So that means if your optimal solution for one variable is not bending, then your actually reduced cost should be 0. So now let's see the tele company case again. So if you look into one optimal solution for our original LP model, the optimal solution is 70-20. If you check the constraints under the optimal solution, you can see you have the two constraints. They're actually bending with the equality constraints. So that basically means that you use up your resources or you take the constraints fully occupied. And then you consume 110 units for department 1 production hours, and you use 20 out of 50 possibilities for XC's production. So that's two constraints are not bending. So you can see the blue constraints, they are not bending, and the orange constraints, they are bending. So we introduced two names or terms, bending constraints or non-bending constraints. We will use them in the following discussion. So we can judge if the constraint is bending or not bending in different places. For example, in the answer report, you just look into the status. Directly will show you this constraint is bending or not bending. And we also mentioned you can look into the slack values. If the slack values are 0, then that's bending. And you can also compare the final value and the constraint of right-hand side. If that's not equal, then that's bending. If they are equal, so that's not they are bending. And if you look into the shadow price, you can also see if the shadow price equals to 0, then that's not bending. So we may explain this again. So here I can just briefly tell the story. So if you have extra capacity available, that means you can continue to produce more units, but they will not actually create more value or profit for you in this example. And for the bending constraints, your shadow price actually is positive. That means you can invest on this bending constraints. You may have chance to create more contributions. So that's just a very informal and brief talking. You can see that later when we talk about shadow prices. So now we come to see the right hand side. So what happens when what happens for the optimal solution if you change the right-hand side of your constraints? So in order to answer this question, we need to actually use a value in your sensitivity report, which called shadow price. Then now we define the shadow price as the change in the objective function value for a 1 unit increase in a constraint of a right-hand side value. So now let's see the shadow price formula. Again, we look into the Tele company case. So this is on the right-hand side, you see the sensitivity report. We highlight the values which are interesting. You can see here. So first, let's see if a constraint is not bending. So first, you find the not bending constraint. So you can see the final values and the constraint right-hand side values. Now you can decide this column, and you find these two constraints not bending, this not bending, and it has a shadow price of 0. Then you can also evaluate by the shadow price, and then you can see if you change the right-hand side of these two constraints within a allowable increase or allowable decrease, the optimal solution will not be changed, will not be affected. So that's the first conclusion. By changing the right-hand side, the objective value will not change as long as the increase or decrease in the right-hand side is within the allowable increase or decrease range. So we actually can see we take one example, for example, for the department 1 production hours. So if we change the value for the right-hand side, so if we name it as a B1, so right-hand side right-hand side for constraint 1 BI, if you change BI in the range, so you can increase, I probably wipe it. So if you increase B1 to infinite level, the optimal value will not change. So we can actually see that from the result. So you already have 120 hours, but under the optimal solution, you only used 110. So there are already 10 units extra. So if you even increase, you give more hours, your optimal solution will not be changed. So that's why we got actually the allowable increase is infinite. And on the other hand, if you decrease the B1 10 units or less than 10, for example, we take 9.9, within this range, actually your optimal solution will not change because your shadow price is 0. Now you are 120. If you change to 110 and 0001, so it's just slightly bigger than 110, actually you can see you actually still have the original optimal solution by consuming 110 units of production hours. So similar for the customer production capacity constraint, so you can look into that yourself. The interesting part about the shadow price is for the bending constraints. So here we look into the two bending constraints in the example. By changing the right-hand side, so these are the right-hand side, and the magnitude of the change in the objective function is given by the shadow price. So that means, so here we first look into what's the meaning of the shadow price. So you have 90 units production hours in the department 2, and then you use all these production hours up, and then the shadow price 10 means if you would like to invest on the extra capacity, you actually have the potential to increase the optimal value of your contribution margin. So your Z value may be increased by 10 units if you increase plus one more B2 plus 1. And then, so that's basically the shadow price means also the maximum value you can invest on one extra unit capacity. So it's the same for the Astra's production constraint, capacity constraint. So within the allowable increase and decrease, the location of the optimal corner point changes, but it's still the intersect of the same constraints. So that's the meaning of the banding constraints, allowable increase and decrease. So you can see within this change, so the shadow price will be same, basically. So you can actually change B2 to B2 plus 5 or B2 to B2 minus 20, and your shadow price will be same. Optimal value will be affected the same. So the third bullet actually explains within this given allowable increase or decrease range, so the optimal solution will stay in the intersect point of the two constraints. So that means that your optimal solution is still determined by the two constraints here, constraint 2 and constraint 3. Now we can actually summarize the result about right-hand side constraints. So change of the right-hand side could affect the feasible region. That's obviously because you change the value of your constraints, the constraint function. So location of an optimal corner point changes if the right-hand side of a banding constraint changes. So again, if you change the banding constraints, right-hand side, it basically moves up and down. So of course, the intersection or the corner point will be affected. So we can just randomly sketch an example here. So if you have a constraint with two main corner points, so if your optimal solution is B, now you can see if you that means both constraint AB and constraint BD, they actually are the banding constraints. So if you change the right hand side of AB, so it means you actually move up on the line, but given the allowable increase and decrease, you actually can see the optimal solution will still be in the intersection between AB and BD. So the shadow price is the change in the objective function for a 1 unit increase in a constraint value, and applies only within a allowable increase and decrease range. So that's actually how they will affect your objective function value. So the sensitivity report can be used to find the interval at which calculated shadow price apply, or alternatively, how much can the right-hand side be increased or decreased without changing the shadow price. Furthermore, we can see the sign of the shadow price depends on what kind of problem or LP model you have. For example, we can categorize the sign of the shadow price by the objective function type and your inequality type of your constraints. For example, in our complementary case, you can see our objective is to maximize total contribution margin, and all our 4 constraints are less than or equals constraints. So in this case, for banding constraints, your shadow price should be positive. All the non-binding constraints should be 0. And on the other way, if you have a minimize objective function and less than constraints, then you actually will get a negative shadow price for the binding constraints. So this can be interpreted because you actually purpose is to reduce the objective function by relax the constraints. So relax the less than or equals constraints equals to increase the value of b, the right hand side. So then your objective function value will be reduced. So that's a minus sign. So on the other hand, if your problem is greater than or equals to constraints, and your objective is to minimize objective function, minimize cost or something, and then if you relax your constraint, or you will say invest on your constraints, then equals to you should actually also increase the right hand side of your constraints. Then it will cause a increase of your objective function. That actually means negative impact to your target. So, and then we can see the if your constraints are inequality greater than or equals your objective, or change your color. So this two combination, and now you can see the shadow price. The sign of the shadow price should be minus. This also can be explained because if you increase the value for the right hand side, you actually will cause the reduce of the objective function. So that's why you have a minus sign. So you can continue to see if your constraints are equals constraints, but basically they all should be binding, then actually your constraints can be negative or positive. So now let's see another point in the sensitivity analysis. So we actually can also use sensitivity analysis table or report to show or to judge if your problem, your LP model has an alternative solution or not. So first, let's say we take one example. Consider the case where the coefficient of XA were decreased from 20 to 10. Another way we see you got a new objective function, which is zeta equals to 10 times XA plus 10 times XB. If you remember, we actually have an initial one, 20 XA plus 10 XC. Now the question is, what corner points are the optimal solutions? So by changing the coefficient of decision variables, now you can see the slope of your objective function changes. Basically, now you can see initially, so now you have the new objective ISO len, so ISO len, which actually is a flatter than previous one. Previous one probably is like this, just pass the optimal solution 70-20. So now the question is actually your objective function parallel with one edge of your feasible region. So now you can see the both point 60-30 and 70-20 give you the be the optimal solution. So now the question is so now you actually can see f or zeta 60-30 is 900 and 70-20 also equals to 900. So these two solutions are both are equal, same. Then the question is there any other point with the same objective function? Is there any other optimal solutions? So let's see the next slides. So now let's see, the optimal solution is reported as 70-20 and in your report. Now you can see already changed the objective function. If we solve the LP model in Excel server again, they actually report the same original optimal solution. But actually it could also be 60-30, as we said, the optimal objective value now is 900. So in this case, a allowable decrease for the coefficient of XA actually is 0. So this 0 means if we continue to decrease the coefficient of XA slightly, you will get a new optimal solution, 60-30. You can give it a try. If you change this value into 9.99 or something, and then you just get a new optimal solution, 60-30, reported in your sensitivity report, in your solution. Therefore, we can actually conclude if we just decrease or increase the coefficients of the decision variables, when you see a 0 in the allowable increase or allowable decrease, actually you may have an alternative solution. So if you just increase or decrease a little bit, you will get reported a new optimal solution. So alternative solution, we try to summarize the general insights. So first, if there is 0 in the allowable decrease or allowable increase for objective function coefficients, that means you may have actually several optimal solutions. So it's called alternative solutions. Here we actually, this conclusion is based on assumption your solution is not degenerated. So we'll not actually cover degenerated solutions in the lecture. So this is not required, but you get a supplement to explain what is degenerated solution if you're interested. So if we have alternative solutions, the sensitivity report applies only to the solution that the Excel has found, and you do not actually see the extra or alternative optimal solution. So you have to be cautious to look into other optimal solutions may exist. And then the last conclusion, if there is no 0 in your allowable decrease or increase columns, then the optimal solution is called unique. So this is actually very important, how to judge the optimal solution is unique. So far we have introduced all the different elements in the sensitivity report, but I know there are a lot of small minor things, a lot of numbers. So the best idea is you try to do exercise to look into the sensitivity report and answer report for each mini case examples, and try to evaluate or judge the different possibilities. So in the Zoom meeting, we will actually take another example. We will do a quiz to test if you understand all these values or the different concepts or terms, and then we also look into the case, the mini cases, to see how we actually evaluate the optimal solution and how to do a sensitivity analysis.